Okay, welcome back to Real Analysis. We've been spending the first couple of weeks constructing the real numbers, and now we're going to turn to a particular proof technique that's going to come up a lot as we move forward, and that's the principle of induction. So today's lecture is completely about induction. And once we have established this proof technique, we'll be moving into Chapter 2 of the textbook, which will be learning about the topology of the real line. Okay, so let's begin. So many of you have encountered induction already, perhaps in a calculus course or maybe discrete mathematics. But I want to say a bit about induction here, because not everybody's seen it. And there are some subtleties which I think would be good for us to explore. So what is induction? Well, induction actually takes a couple of different forms. You can think of it as a proof technique, but it really, you should think of it as an axiomatic property of the natural numbers. So let's begin with the natural numbers. So let me just remind you what we're going to think of as the natural numbers here. Natural numbers I will think of as starting with 1, and it's the positive integers, if you like. And we'll think of these as the natural numbers. Actually, the fact that this particular set begins with 1 is sort of inconsequential. We could also develop what we're going to talk about starting with 0, but I'm going to think of starting with 1 here just because I'm going to think of these as indexing statements that we want to prove. So let me start by telling you one property of the natural numbers that might be, hopefully, self-evident. And that's something called the well-ordering property. So what is the well-ordering property of the natural numbers? And if you don't mind, I'm going to abbreviate this by WOP, so I don't have to rewrite it. The well-ordering property of the natural numbers says the following. It says that well, first of all, it says that n is well-ordered. So I have to tell you what that means. So what does it mean for a set to be well-ordered? Well, it means that if you take any non-empty subset, so every non-empty subset of the natural numbers has a least element. Okay, so the natural numbers are endowed with an order, which is the one you usually think of. 1 is less than 2 is less than 3 is less than 4. Okay, if you're worried about that axiomatically, you could begin with constructing the natural numbers using Peano's axioms. Okay, if you want to look that up, Peano is spelled P-E-A-N-O. There are 5 axioms for the natural numbers. And it usually begins with, actually in most versions of Peano's axioms, it begins with 0. You postulate the existence of a 0, okay? And then you postulate the existence of a successor function, which basically tells you what the next thing is. Okay, so 0 has a successor, we'll call it 1. 1 has a successor, we'll call it 2. 2 has a successor, we'll call it 3, etc. Okay, and there's a few more axioms, but starting with those axioms of the natural numbers, they're called Peano's axioms, you could develop an order. Okay, so 4 is bigger than 1 if it is an eventual successor of 1. Okay, if you want to go back that far. Okay, we're going to just assume that we have an order already on n, and a particular order, and the claim is that that is a well-ordering it has this special property. How many people think this is sort of a self-evident property of the natural numbers? Not necessarily self-evident? Okay. We're going to take it to be an axiom, okay, for the natural numbers, okay? Okay, well, what you may not realize is that this is, in fact, related to the principle of induction. So let me just summarize what I just said here. You can think of, so let me remark, you can take the well-ordering principle to be an axiom. That is something we assume, we do not prove. It is something we assume about the natural numbers. Now, it is, I claim, related to the main topic of this course, which is the principle of induction. How many people have actually encountered induction in a previous course? Okay, most of you. What is the principle of induction? Well, it says the following, which I'll let you decide if it's self-evident. Suppose I have a subset. So let's let S be a subset of the natural numbers with two properties such that two properties hold. The first property is that 1 is in the set. And the second property is if some number little k is in S, then also little k plus 1 is in S. So this is, I'm going to put commas here because I haven't finished the thought, such that 1 is in the set, and if something is in the set, then its successor is also in the set. Okay? If you have a set with these two properties, then I claim we can conclude something. Then, in fact, what kind of set must S be? If it contains 1, and if it has the property that if it contains something, it contains something plus 1, what set must it be? Must be all of the natural numbers. Okay. This is the principle of induction. This is the principle we want to explore today. How many people would say this seems self-evident? Self-evident? Do you think it requires proof? How many people think it requires proof? Maybe, yeah. I mean, so Moira, would you say this requires proof? Would you say, what did you think about the well-ordering principle? Does it require proof, or was that self-evident to you? Just give me your opinion. Yes, okay, so you say it seems more self-evident than this. How many people think that this property seems more self-evident than this one? How many people think this one seems more self-evident? Vote. Vote, everybody vote. Form an opinion. How many people think the well-ordering, if you were willing to take something to be axiomatic, which would you rather take to be axiomatic? This property, well-ordering principle, or the principle of induction? Let me see by a show of hands. How many people would vote for this one? How many people would vote for this one? Okay, Sam is happier with this principle, yes? Well, good news for everybody is, in fact, these two properties are, in fact, equivalent properties. So you could take either one to be axiomatic, but we will take one of them to be axiomatic, okay? So here's the thing that's interesting is, and in fact, I'm going to, if you don't mind, abbreviate this by POI. So here's an interesting fact. The well-ordering property and the principle of induction are, in fact, equivalent. Surprise, perhaps. Okay. We'll take take either one of these. We'll take since most of you were happier with this, we'll take the well-ordering principle to be well-ordering property to be axiomatic. Okay. Okay. Let me, in fact, prove one of these directions, and then maybe later on, if there's time, I'll prove the other direction. Okay. So here's a proof that, if you like, the well-ordering principle implies the principle of induction. Okay. So to make most of you happy here, I'm going to prove that if you assume these two properties about S, then it must be the natural numbers. Would you agree? That's my burden. Okay. And I can assume that every non-empty subset of N has a least element. Okay. So this is how it's going to begin. So let's begin this proof. So suppose you have a S with the given properties. Well, either S is N, which is what we want to show, right? Or it's not, and then maybe we could get a contradiction, right? So let's do this by contradiction. Usually you clue the reader that you're going to do a proof by contradiction. Suppose S exists with the given properties in the principle of induction, but suppose S is not the natural numbers. Everybody agree this is how I would begin a proof by contradiction. Okay. Where's the contradiction going to come? Where's the contradiction going to come? Maybe I will do some scratch work here, which does not belong in your notes, but we're just going to think about this a little bit. So we have some mysterious subset of the natural numbers. Natural numbers maybe begin like this. They don't maybe begin like this. They do begin like this. And S has a curious property that it's not everything, okay? But it does look like that picture. It's just not everything. So it does look like have those conditions, A and condition B. So maybe, could S look something like this picture? No, why not? Okay, because 1 is in it. So we're just getting a feeling for why this is going to be true. So 1 is in it. And maybe, let's say, 2 is in it also. Yes, Emil? Oh, well, we are assuming that because I'm assuming the hypotheses of this. So the question was, why does S have to be a subset of N? Because that's part of the hypothesis. Okay. What we want to show is that, in fact, it's everything. So could S be this picture? Why not? And don't tell me by induction or the principle of induction. We're trying to prove that. 2 is an S, then 3 is an S. Okay. Sure. Okay. So now you're saying this has to be in, right? And then you're saying because of that, this has to be in. This has to, okay, et cetera, et cetera. But that feels to me like I'm going to have to appeal to this over and over and over and over and over again. Somehow that feels unsatisfying to me, right? Because in some sense that's what induction says. But can you do this in a way that I don't have to appeal to this step over and over again? Steve?
Could you say that maybe there's something in N that is not an S and then try to figure out, trace it, go backwards?
Okay, question was, could you look at everything that's not in S and start there? I like that idea, Steve. I like that idea. Why do I like that idea? I like it because it allows me to get a handle on something very specific where I can hope to get a contradiction without having to appeal to property B over and over and over again. Okay? Okay, so let's do that. Let's give it a name. Then let's let A be n minus s. What can you say about, okay, I haven't finished this sentence because normally I would write let A equal n minus s, but I'm going to make my writing a little more streamlined by defining this in the course of saying something else. Then let A be n minus s. What can I say about the subset A? Yes, thank you. This is the subset A. There might be other things, right? A has a smallest element. I heard many of you say that. Maybe some other stuff here. Interesting. Yes, so we are appealing to the well-ordering principle. That's a nice thing, right? This is why I won't have to bootstrap B over and over and over again, right? I'm appealing to something that will make my life a lot easier. Then A, which I'm defining to be n minus s, and I might tell the reader this, has a least element by the well-ordering principle. It's courtesy to remind the reader of this if they don't see it, because isn't this a crucial ingredient? Okay, good. Now what? What about this least element? In this picture, that least element is here. So what? Oh, interesting. So you're saying take this and look at its predecessor. It's not going to be an A. Why? That's the smallest. Good.
And so then since that one's true, then since those two properties hold, we know that if you add one to it and it is true, so then it's not an A.
Okay, excellent. So the comment was, look at the predecessor of this least element. That is not an A. But then, therefore, it must be in S. But S, by property B, has the property that its successor must be in S. But then that would contradict the fact that it's in A. And we're done. Do you see that we didn't need to hop over and over and over again? We use the well-ordering principle here to get directly to the crux of the matter. So then A has a least element by well-ordering principle, comma, call it a name. Let's give it a name. How about N? Now, what did you say about N? Whatever this thing is, it's N. Look at N minus 1. Okay. Now, we have to be a little careful here. How do you know that this thing has a predecessor, N minus 1? Excellent. So we have to at least be sure that N isn't 1. But we know N isn't 1 because 1 is in S and therefore is not in A. Okay, so call it an N. And so here, this is something to remind the reader. Notice, N is bigger than 1 because 1 is in S. So 1 is not in A by property A, if you want to remind the reader. Everybody happy with that? N is bigger than 1. Good. So what do you want to look at now? We want to look at N minus 1. What's another way to say look at N minus 1? Consider. Yes. Consider N minus 1. We might not have to say that, in fact, if we just cut to the chase. What about N minus 1? Well, it's not an A, therefore it's an S. Well, I'll just tell you to consider because it's a gentle way of saying pause and think about this for a second. Consider N minus 1. It is not in A because it was the least, N was the least element, so it's in S. Oh, okay. But property by property B, n minus 1 plus 1 should therefore be in what? Is in S, which implying n is in S, a contradiction. And if you think the reader has any chance of not seeing the contradiction, you could remind the reader it's a contradiction because n was in A. Okay. So what does this mean? This means that the original statement is in fact true. Therefore, so it now initially, if you assume the reader hasn't had that much practice with these kinds of proofs, you might want to remind the reader the contradiction implies that the thing you're trying to show holds. But as you get more mature, stopping with the contradiction should be enough. Okay? Yes? Does it imply that A is empty? Yeah, we assumed it was not empty. Yes, very good. So the question was, should I not have reminded the reader that A is in fact non-empty? And that would be good, actually. Or I guess you could say this shows that A is empty, and therefore S must be all of N. Yeah. Which would be the most elegant way of saying this? That's the question to ask. Step back a second. What would be the best way to say this? In order to say it has a least element, I have to assume that it's non-empty. So I think I want to tell the reader, because we started this way, suppose S exists with the given properties, but S is not N, then A equals N minus S is non-empty. That's the thing that follows. And therefore, so it has a least element. Okay? Everybody good with that? Yeah. So this also points out another thing I think I want to emphasize, and that is, when you're doing a proof or you're doing any kind of mathematical writing, it's always a process of revision, right? You see a way to the solution, but then you see a better way of making the proof airtight and clear. So should not be surprised if you come back, and you have to come back a few times and clean things up. Okay, excellent. So the well-ordering principle is the foundation of induction. Okay, so let me say a few things about the method of establishing a proof by induction. And then we'll do some examples. So if you want to do a proof by induction, so what does this have to do with the method of induction? What you usually want to use induction for is to prove a whole series of statements, infinitely many statements, all at once. Okay? And those statements are indexed by the natural numbers. There's a first statement, there's a second statement, there's a third statement, etc. Okay? And so normally you think of a collection of statements, which I'll just call P of n. Let P of n be a statement, some statement that is indexed by the natural numbers. Okay. And maybe I'll say let P n be statements, statements indexed by the natural numbers. And so the idea then is to show P of n is true for all n. Now, what would that mean? What I'm really looking at is a set. I'm looking at the set of all statements where P of n is true. That's a subset of natural numbers, isn't it? And I will show that the statement is true for every natural number if I show that it's true for the first, and if it's true for the kth statement, then the k plus 1th statement is also true. Okay? Do you see how we're really just using this fact? So the idea is to show P of n is true for all n. For all n, we'll show two things. The first thing is that P of 1 is true. This is often called the base case. And we want to show that if the kth statement of true is true, if P of k is true, then P of k plus 1 is true. Okay, and this also has a name. It's called the inductive step is this step, right? So this is the inductive step. Okay. Base case, inductive step. The inductive step is this entire piece right here. What assumption do you normally make when you're doing the inductive step? You're assuming something, right? And this has a special name. We call it the inductive hypothesis. Okay. You'll often hear that, the inductive hypothesis. All right. So, the principle of induction says this is enough to show that P of n is true for all n. Okay. So to show this, we'll show this, and I just want to conclude then by saying then the principle of induction implies that this is true. Or then by the principle of induction, Pn is true for all n. Okay. Okay, that's the method of proofs by induction. And basically what we've just done is basically looking at the set of all n such that P of n is true. That's really what we're doing. So behind the scenes, we're looking at this set and showing that S is n. And showing, we're really considering this set and showing S is n. Okay. Okay. I should probably mention that there is another version of induction which is related to this one. It's completely equivalent, but it looks stronger, and so it's called the principle of its strong induction. And the principle of strong induction has the same hypotheses here, except B looks slightly different. Okay? So strong induction, we're going to use B prime instead of B, where B prime is the statement that if not just the kth thing is true, but you could assume that everything previous to that is also true. If P1, P2, ... through Pk is true, then P of k plus 1 is true. The principle of strong induction allows you to assume that everything up to the kth statement is true. You can see why that's equivalent, because if you showed that 1 is in the set, and then each successor of anything in the set is in the set, then that's the same as if you've shown up through k that this is true, then you have everything from 1 to k in the set already. Okay. So you're welcome to use the principle of strong induction if you need to. Okay, let me make a few other comments about style when you're doing a proof by induction. So it's customary when you're doing a proof by induction to warn the reader you're about to do a proof by induction. Okay, just like proofs by contradiction, you usually tell the reader. What do you think you want to tell a reader if you're doing proof by induction? Aside from the fact that it's an inductive proof, you might want to tell them what? Yeah, what you're inducting on, or in other words, what is the index that you are looking to make this induction argument hinge upon? So let me just mention some words about style. So at the start, you basically should tell the reader it's a proof by induction. And you usually tell the reader what it's inducting on, by induction on whatever. And what this means is usually you tell the variable that's the index that it's the variable that's being inducted on. So in this case, we're inducting on n, which variable serves as the index of a bunch of statements. Usually tell the reader that. The other thing is you usually separate out both these two hypotheses. What you're trying to establish them so that you can use the principle of induction. So you usually tell the reader that you're doing the base case and the inductive step. So you indicate. So you should tell the reader when you're doing both A and B, the base case and the inductive step. And both of these terms, you should assume the reader knows what they mean. So often you might say the base case is, and you don't have to define base case. So star just means you can assume these terms are understood. For the mathematically literate reader, they will all have seen this. Okay. Okay. And it's helpful to, when you're done, remind the reader what the conclusion is. I'm realizing this might not be so visible there. Remind the reader of the conclusion at the end. Because these are sometimes long arguments, and you want them to realize, summarize where you've been. Okay, let's do some examples. So here's an example. This is one of my favorite proofs by induction. Absolutely favorite. Some of you may have seen this as in, sometimes it's done in the core classes here. Suppose I have a chessboard. So this is an 8x8 chessboard, but in general, we're going to look at 2 to the n by 2 to the n chessboard. So every 2 to the n by 2 to the n chessboard, this is, let's say, 8x8 here. In this case, 8x8. That's a real chessboard, isn't it? Something can be done, I claim. So if I take a 2n by 2n chessboard with one square removed, so every 2 to the n by 2 to the n chessboard with one square removed can be tiled by L-shaped tiles, by figures that look like this one. Okay. L-shaped tiles. Okay, is that true? How would we show that? Well, here's the thing. If you're looking at this particular chessboard and I say remove a square like here, so how would I tile the rest of it? Now, the thing about induction that's really amazing is the actual statement or statements you're trying to show, you might have no idea how to do it, right? No idea. But what's great about induction is often you don't need to have insight to do the problem, right? Right? You're sort of replacing the fact that I need to have insight about some 8x8 board by the fact that I know if I can do a 4x4 board, I can do an 8x8 board, right? That's sort of the hope, right? Maybe I'm going to induct on n here if you have some induction, okay? So let's just see that this is true. First of all, for the base case. Well, first let's decide what I'm going to induct on. N, good. So let's do proof, and it'll tell the reader by induction on N. Okay. Okay, so for the base case, so I'm just telling the reader, I'm doing the base case. Is it true that if I have a 2 to the 1 board by 2 to the 1 board with one tile removed, that it can be tiled by a, yes, okay, that should be evident. A 2 by 2 board, I'm not even going to write all this out, okay. We see that if you remove this one square, there are 4 cases, but they all kind of look like this one, the statement holds. And I'll just say as desired, because I'm reminding the reader this is really what I wanted to show. Okay? You could draw all 4 cases if you want. Okay? Or say by symmetry, right? Yes, Bonnie. Yeah, the question was, does it matter that your base case starts with 1, or can it start with other things? And the answer is, yeah, it can start with other things. There was nothing special about 1, except that it was the least element of the subset that I wanted to show a bunch of things were true for, right? So if I, for instance, wanted to show that some statement holds for all statements indexes bigger than 50, my base case would start at 50. Okay, if I wanted it to. Okay, good. That's the base case. I've done the base case. Hurrah. Okay, now the question is, if it's true for the kth case, can I show it's true for the k plus 1th case? So let's just look at our picture here. Here is the 8x8 board playing the role of the k plus 1th case or the kth case? K plus 1, that's what I'm trying to show, right? So if I know it's true for a 4x4 board, will that help me show it's true for the 8x8 board? So here's the other part of the process of induction is you're often looking for the smaller cases embedded within the big one, right? So here, I have an 8x8 chessboard. Are there some natural 4x4 chessboards here I might want to look at? Yeah? Where? Maybe this 4x4? No? Why not? It's a 4x4. No, okay. Maybe this one. This seems kind of natural, right? Oh, ooh, interesting. Okay. So, if it's true for a 4x4, that if I remove a square, that I can tile it by L-shaped tiles, can you see how this would help me do one of these 4x4s? The inductive hypothesis would let me do this part, wouldn't it? I don't even need to know how it was done, right? That's what's beautiful. No insight needed, okay? But I can do this somehow, yes? So can do. By the inductive hypothesis. Okay. Now, can the inductive hypothesis enable me to do these parts? Not yet. I got to remove a square from each of them. But maybe I'll do that in a way that it forms an L-shaped tile. Yes? Can you do that? Yes. In fact, how about these three squares right here? Would you agree they form an L-shaped tile? And then everything else I can do. Right? Agreed? Induction. Okay, that's the ethos of this method. And this is almost beautiful enough that you don't have to write out the argument, but I'll trust that you can write it out carefully. I'll just summarize it here, right? For the inductive step, what you really want to do is, okay, so this is where you have to be careful. So I'm gonna try to be very careful about this because there's often an error here that people make without realizing. I'm going to, I want to leave the principle of induction up, and I actually want to leave that up too. So I'm going to erase this if you don't mind. So I'm about to show B. What can I assume? I can assume that the statement holds for K, and I'm trying to show it's true for K plus 1. So here, I can assume, so for the inductive step, so I'm going to be very explicit here, we can assume any 2 to the k by 2 to the k board with a square removed can be tiled, etc., by L-shaped tiles. That's what we can assume. What are we trying to show? What should I start with now in order to finish, to do part B here? What should I start with? A 2 to the k by 2 to the k board? Build up on it? No. What should I start with? A 2 to the k plus 1 by 2 to the k plus 1 board. Very, very important distinction. Many of you I know are tempted to start with a 2 to the k by 2 to the k board because that's part of what you're assuming you know is true. But what the problem is asking you to show is that the statement is true for any 2 to the k plus 1 times 2 to the k plus 1 board. So you have to start with that. So let's start with, consider a 2 to the k plus 1 by 2 to the k plus 1 board. With one tile removed, with a square removed. Okay. And now describe this process. So I'll let you do that, but we'll say we can divide the board into 4 parts. One with with the original square removed. And 3 with 3 full 4 by 4 2 to the k by 2 to the k boards. I might as well give these names. Let's say let's call this okay, so maybe I'll just say the first can be tiled by the inductive hypothesis. And then the last 3 can be tiled once you do what? Remove a square from each in an L-shaped manner. The remaining 3 can be tiled by the inductive hypothesis once a tile has been removed. Let's remove one in an L shape. See figure. Okay, this is how I would write it out. Okay. Oh, great. So then the whole thing can be tiled. So the new board, so the large board can be tiled. So the 2k plus 1 by 2k plus 1 board can be tiled. With one square removed, can be tiled. Okay, great. Have I completed what I set out to do? I've shown the base case. I've shown the inductive step. And so now, by the principle of induction, I'll just insert a little thing here. By the principle of induction, the statement holds. I would probably write out the statement again, but for the purposes of board work, I will just remind you that the whole statement holds. Okay? Now, here's what I want you to notice. I'm going to point this out here because in some other cases it might not be so obvious. But do you see how this would be different if you had started with a 2 to the k by 2 to the k board, which is the wrong approach? Do you see what would be wrong about starting with a 2 to the k by 2 to the k board? Somebody tell me what's wrong with starting with the 2 to the k by 2 to the k board. Someone I haven't heard from yet. Yeah, still on. You're starting off with what you assumed, but there's nothing wrong with that. It's true that for a small board, you can tile it if you remove a square. What's wrong in terms of establishing the inductive step? What's wrong with that? Yes. Excellent. Remind me your name. Lindsay. Yes. Lindsay's point is you want to start with a general large board, a 2 to the k plus 1 by 2 to the k plus 1 board. And it's not obvious if you start with a 2 to the k by 2 to the k board, let's call it a small board here. It's not obvious that if you do this and then you throw together some extra pieces like this, that you have a general enough board, right? The general board is this one in which you find the smaller pieces to appeal to the inductive hypothesis, the inductive step, right? But if you start with this, how do I know that every tiled small board, when you add pieces to it in some prescribed fashion, it'll result in a large tiled board, but how do I know that every large tiled board can be divided this way? Do you see the distinction? You should start, if the assumption is the small board can be tiled, but you should start with the large board and work from there, okay? This may seem pretty obvious in this example, but on your homework, there's a problem where people often mess up the construction by making this error, okay? So the homework, I think, asks you to show that every finite set of real numbers contains its supremum. So every finite set of numbers contains its supremum. Let's just get a hint at how you might prove that. Okay, so you have a finite set of numbers. That seems to be a very general statement, right? A statement about a bunch of numbers. In fact, a finite number of them. So that's a bunch of statements you're trying to prove, right? So you might think, oh, I could prove this by induction. So what should I induct on? How about the number of things in the set? Good. Let's call that n. So, I assume you'll do the base case. But now, if you're trying to do the inductive step, what should you start with? A set with how many elements? Or k plus 1, right? And then find the k element set within that. Now, the mistake people make every single year when I assign this problem is they'll start with the k element set and add one element to it. Some of you are thinking, well, I don't see the difference. Well, there's a philosophical, I guess, difference in that you aren't necessarily sure that if you don't start with a k plus 1 element set and find a k element set in it, it's not the same thing to say that you start with a k element set, you add one thing, that's general enough, although it happens to be. Okay? Okay, so just be careful of that error. Okay, any questions so far about the principle by induction? Okay, let's take a couple of minute break, and after the break I want to show you some more features of induction, also some other common errors of induction. All right? Yeah.
I have a question about the principle of induction.
Yeah.
Making it a subset of n, wouldn't that make it also a property? Isn't that a property of S also? That it's a subset of n?
It was I'm not sure what your question is.
Like,
We're assuming S is a subset of n.
but wouldn't that also kind of, I guess, I don't know. I feel like that's also a property of S that we're just not saying it's a property. We're just
That what's a property?
that S is a subset of n.
Yeah, this is any subset of n. In other words, you give me any subset you like. This is a statement about subsets of n.
But here's my question: couldn't we generalize this to make it true for any set S that has those two properties? Why do we need to restrict it to just?
Oh, because we haven't talked about this yet, but it deals with the issue of countability.
Okay.
So later on, we'll see that you could do this for other subsets of other things.
Okay.
But you need something stronger, which is not logically equivalent to induction. It's called the principle of transfinite induction.
Okay.
Yeah.
Okay. Also, the principle of
Yeah.
strong induction versus the principle of induction, they don't imply each other, do they?
They are. They do.
Okay.
Clearly, strong induction implies induction.
Oh,
And then the other way you can show by bootstrapping,
Okay.
by induction.
Okay. All right.
Yeah.
Okay, thanks.
Okay, let's resume. Let's do a few more proofs by induction. So here's a theorem, which many of you have seen before. But let's prove it. Prove that if I take the following sum, which I'll call S sub n, and it's the sum of the first several odd numbers up through 2n minus 1, prove that this is a perfect square. So let's just start naively and see where we can go with this. This is a statement that's clearly indexed by the natural numbers. So I immediately think induction, right? And the beauty is I don't need to have insight. Okay? Now, if you had insight, you could certainly do this a different way. But, I might start like this. In fact, I might just call this a scratch proof because we're not sure this is going to work, but let's just see. Okay? Here we go. For the base case, is it true? The base case is n equals 1. Is this true? Base case holds since what? S1 equals 1 is 1 squared as desired. A square is desired. Is this a sentence? Yes. Base case holds since blah. Yeah. Okay. Period. Okay, great. That wasn't so bad. Inductive step. For the inductive step, well, we can assume Sn is a square. If it's a square, I can write it as a natural number squared, right? So what square is it? Maybe, let's say k squared for some k. Right? Agreed? Yes? It's some square. Okay, so what should I start with now if I want to show the inductive step? I want to start with S sub n plus 1. Yes, I guess I'm inducting on n. So we want to show, you might as well tell the reader, we wish to show Sn plus 1 is a square. Okay. Well, let's just write it out. Here we go. Sn plus 1 is, now, it would sure be nice if I use the inductive hypothesis somewhere. Sn plus 1 is the sum of the first bunch of natural, of odd integers. And you'll notice it goes up through 2n plus 1. And the term right before it is 2n minus 1, isn't it? So do you see the inductive hypothesis here somewhere? Really? Where? Right here. So this is S sub n plus 2n plus 1, which is, S sub n is a square. This is k squared plus 2n plus 1, which, not so helpful. Gosh darn it. I sure was hoping that this inductive hypothesis was going to help me. It doesn't look like it's a square of anything that I know of. You're all smirking. You're laughing at me. Why are you laughing at me? I tried. This is the best I could do with what I was given. What was I given? Well, the inductive hypothesis, assume Sn is a square, some square. But it's not really strong enough to help me here. What could I do? I can strengthen something. It's not strong induction, but it is specifically strong induction. But what could I do, David?
Strengthen your claim. Say that S sub n is a square equal to n squared.
Oh, interesting. Interesting. Notice that the problem was I had too weak an inductive hypothesis. It's too weak. Too weak to give me what I want, because this is a bunch of question marks in a row, right? And a period after that even. Look at that. Wow. Okay. Too weak. But David says, hey, I can strengthen my inductive claim. Now, it better be true, whatever I strengthen it to, right? So, assume Sn is a square. What would you like to strengthen the claim to?
N squared.
Yeah. Is that true? Is it true? Do you want to just check? Is it true for 1 still? Yeah. And you can check a few other cases to begin to see that it might be true for more than just 1. But, okay. And once you have that, let's strengthen. We're going to strengthen and this is often a very key technique with induction, is sometimes you have to prove something more, and that allows you to do more because you have a stronger inductive hypothesis. This is what's amazing. Let's strengthen this to the claim. Strengthen claim. The claim is it's actually Sn equals n squared. And now notice what happens here. This would change to what? N squared. And now is this a perfect square? Excellent. N plus 1 squared, which I will now remind the reader is a square as desired. Everybody happy with that? Okay, that's a key technique. Strengthen the induction sometimes if you need to. Okay. Hey, I like that. That's great. Let's see what else we can prove with induction. You can prove all sorts of cool things. Chessboards, natural number claims. Let's prove the following claim. Theorem. All natural numbers are even. All natural numbers are even. Okay, we can prove anything by induction. Proof by induction on n. What's n? Oh, I haven't even said what n is. Well, it doesn't matter. I'll prove anything by asserting. I'll tell you what n is. Let's suppose n is the number we're trying to show is even, right? So maybe the way to restate this is every natural number n is even. So I'm going to restate this. Any natural number n is even. There. Now we have an n that we're talking about. Okay. Happy? Okay, here we go. Proof. I'm going to use strong induction if you don't mind. Need something strong to prove this statement. Here we go. Let's assume all numbers less than or equal to n are even. That's by strong induction. Okay. I'm going to do the inductive step, if you don't mind. Base case is kind of trivial. It's irrelevant. You don't need to do it. Notice that if you give me a number n, so I assume all numbers less than, maybe let's make this, less than or equal to n or even. So let's look at n plus 1. Well, let's see. I claim n plus 1 is n minus 1 plus 2. Okay. And by the inductive hypothesis, n minus 1 is even. So n plus 1 is the sum of two even numbers. Nice. As desired. End of proof. What do you think? Aren't you proud of me? Oh, yes. What's wrong with this proof? Jenny. Don't have a base case. Yes. Okay. So, I mean, there's nothing wrong with the inductive step. Would you agree? You can do a lot if you never get this thing off the ground. Certainly lots of implications like this could be true, but the key point is you'll have a problem, won't you? Here, there's no base case, so this is obviously flawed. No! The base case, the problem is the base case doesn't hold. Right? You know, what is interesting, however, is that this proof actually well worked to show that all even numbers are even. Right? Right, you start with a base case of 2, and what it does is it shows that it doesn't do this particular implication. It shows that if k is even, then k plus 2 is even. That's really what we've done, isn't it? Right? Okay. So really, the flaw with this proof is basically in not showing the base case. Happy with that? Okay. Let's do one final thing here. Theorem. Let's show that. Let's go crazy. Let's show that all horses are the same color. All horses, they're all the same color. And like any amazing fact, we can prove it by induction. What do we want to induct on? Number of legs? No, that's a different statement. Okay, induct on wavelength. Yes, very funny. Let's induct on the number of horses in the set. In a given set. Oh, I love this proof. This is great. Okay, we're going to do the base case since you guys are so concerned about the base case. For the base case, with one horse, a set with one horse. Isn't it true that in a set of one horse, all horses are the same color? Yes. Set of one horse, the statement holds. Ah, yes, all horses are indeed the same color in a set of one horse. Love it. Okay, so now for the inductive step, let's suppose let's let S be a bunch of horses. I might as well call H1 through Hn plus 1. Okay. H1 through Hn plus 1. And now I want to find the inductive hypothesis in here, which concerns a set with how many horses? N things. I have N plus 1 things. Oh, well, check this out. Then S prime, which is H1 through Hn, and S double prime, which is H2 through Hn plus 1. Wouldn't you agree that they have one fewer horse? Therefore, the inductive hypothesis holds, and all these horses have the same color. Have n horses, and by the inductive hypothesis, all have the same color. In each of them, the horses have the same color. Have the same color in each set. Oh, great. But clearly, H2 is in both sets. And so all these have the same color as H2, and all these have the same color as H2. So all have the same color as, in particular, H2. Done, as desired. All horses have the same color. Great. We will see you next time. No? Don't end here? What's the problem? Is there a problem here? Because clearly horses don't all have the same color, right? Yes. Okay, but I did do a base case. I did want to show it for all horses of size 1 and bigger. So I did do a base case. Yes, Patrick. Oh, sorry, go ahead.
You didn't actually make an induction hypothesis. You constructed two induction hypotheses out of your induction step. You generated them backwards, which doesn't work.
Backwards? I think I did it in the right order. I started with an n plus 1 set. I found two n sets in it.
But your induction hypothesis would be, let's have a set of n horses, H1 through Hn, not saying anything about Hn plus 1.
Right, but this one has Hn plus 1 in it, and all these have the same.
Not the other one.
Interesting. Yes, tell me what you think. Oh, where did I make that assumption? The comment was, I'm assuming I had at least 3 horses.
Because when you're S prime has at least 2 members, means you're using 2 members. Like if you had 2 horses, you wouldn't be able to split into 2 sets that would overlap.
Ah, interesting. Okay, so the comment was, without realizing it, I've assumed that I have at least 3 horses, because when I go down to these 2 sets, I assumed they overlapped in H2. But there is a case where they don't overlap at all, right? That's the case when you have how many horses? 2 horses, and these end up being disjoint sets. So the problem here is, in fact, that the inductive step fails in a very bizarre way. So here, no. The inductive step fails. And in particular, it fails when n equals 2. Okay? Okay, so there's some things to be very careful of, which you should be aware of as you're doing proofs by induction. And there are a few assignments, homework problems now, that you'll see where you'll find induction a helpful technique. If you're interested in a nice challenge, I encourage you to do this. I didn't have time to do it in class today. I encourage you, now that you know how to do proofs by induction, to prove the other implication that the well-ordering property follows, that the principal induction follows, the well-ordering property follows from the principle of induction. Okay? So see if you can think of a way to prove the well-ordering property from induction. All right, we'll see you next.